Hello everyone. In this video I'm going to talk about the notion of duality in nonlinear optimization. Alright, there is a very step-by-step, clear step-by-step procedure here. So we start from the primal problem. Which is minimizing an objective function subject to some equality and some inequality constraints. So here, because we are dealing with nonlinear programming, even if your variables are bounded, so let's say I have x is greater than or equal to 0. I can translate it into this form, right? I can say minus x is less than or equal to 0. Or if you have a variable which is less than or equal to 0, it already satisfies this template. So this is your first step, primal problem. So based on the primal problem, you have to find the Lagrange function. L is f of x plus lambda transpose equality constraints plus mu transpose inequality constraints. So if you recall, lambdas refer to the equality constraints and mu's refer to the Lagrange multipliers for inequality constraints. So based on the Lagrange function, so this is step 1, this is step 2. Based on the Lagrange function, now what I do, I formulate the dual function. What's the dual function? It's phi of lambda and mu, so it's only a function of the Lagrange multipliers, is equal to minimizing Lagrangian of x, lambda, and mu with respect to x. So here, our only variable is x, and we are trying to find the formulation for the dual function. This is the third step. The final step is to formulate the dual problem. So it's maximizing the dual function subject to mu greater than or equal to 0. This is step 4. Although in linear programming we could guarantee that the solution, the optimal solution to the dual problem is the same as the optimal solution to the primal problem in terms of the value of objective function, in nonlinear problems, in nonlinear optimization, we cannot guarantee that, and we need certain conditions to make sure that the duality gap is 0. So in general, basically, let's remove these two steps. In general, basically, the answer to dual problem only is a lower bound for the primal problem. So solution of dual function in nonlinear optimization gives a lower bound on optimal solution. Let's review it one more time. The solution of dual function in nonlinear optimization gives a lower bound on optimal solution of the primal problem. So dual, primal, nonlinear. These are the keywords here. If you want to write it mathematically, f of x star, where x star is your optimal solution, is greater than or equal to phi of mu and lambda at any point. So any value of your objective function cannot be less than the value of your primal, your dual function. Another fact is primal and dual optimality. If f of x star is equal to phi of lambda star mu star for some feasible solution. Feasible solution means a solution that satisfies all of the constraints. Feasible solution satisfies all constraints. Like x star of the optimal problem, the primal problem. And for some feasible solution, let's say lambda star and mu star of the dual problem, then x star and lambda star mu star are optimal solutions of the primal and dual problems respectively. Let's think deeply about this. So this is a very strong condition when it comes to nonlinear programming. In the linear optimization, it was quite easy to guarantee that it always happens, because when you find dual of dual problem, you come back to your original problem. But in nonlinear programming, that's not the case. In most of the cases, there is a duality gap, and the optimization algorithms that we develop, we try to minimize this gap. So here it tells us if the value of your objective function for the primal problem at a certain feasible point is equal to the value of the primal problem, again at a feasible solution, that point is for sure the optimal point of both of these problems. This is interesting because at the same time, you are not only finding the values of your variables, but also the value of your Lagrange multipliers. Let's say in the supply-demand problem that I mentioned before, if you solve the problem, at the same time you find the optimal value of your supply and demand, and also you find the value of your market price. So at the same time, you're finding some of these real-world variables. So let's look at an example. Before going to the example, let's define the duality gap. So duality gap is the difference of your objective functions for primal and dual. the difference minimizing f of x subject to g of x is equal to 0, h of x is less than or equal to 0, minus maximizing phi of lambda and mu, where mu's are positive, is called the duality gap of the dual problems. So that's just the basic definition. So now that we know about the nonlinear optimization and the duality in nonlinear optimization, let's try to solve an example. Minimizing x1 square plus x sub 2 subject to minus x1 plus 2x2 is equal to 0. x1 minus 2 square less than equal to 2. Alright. If you recall the 4 steps, first step is to find Lagrange function. Lagrange function is your objective function, x1 squared plus x2 plus, let's assign lambda to this and mu to this constraint. Lambda multiplied by the equality constraint minus x1 plus 2 x sub 2 and mu to inequality constraint. Before doing that, we have to write this in the format of less than or equal to 0. So it will be x1 minus 2 s squared minus 2 less than or equal to 0. I just brought 2 to this side. So plus mu x1 minus 2 s squared minus 2. After having your Lagrangian, you define the dual function. The dual function is phi of lambda and mu and is equal to minimum of Lagrangian x1, x2, lambda, mu, but our only variables are x1 and x2. We also know that mu's are positive. So in order to solve this, we use basic algebra. So we find its derivative with respect to x1 and x2. We find the derivative of Lagrangian with respect to x1, which is 2x1, 2x sub 1 minus lambda plus 2 mu x sub 1 minus 2. This is equal to 0. The second one, derivative of partial derivative of Lagrangian with respect to x2. So x2 is more straightforward. 1 plus 2 lambda is equal to 0. Alright. We also have the constraints of the original problem. They are going to be satisfied, right? So we know that this should be a feasible solution of the original problem also. So looking at this, what it tells us minus x1 plus 2x2 is equal to 0. So we can conclude that x1 is 2x2. Or here we all have x1, yep, there we go. Okay, why don't I look at this one at this point? Because I don't want to find the value of lambda. What I want to do, I want to find the value of x1 and x2 as functions of lambda and mu. So given these two equations, I can do that. Let's remove this part that we already used. So 2 mu x1 minus lambda minus 4 mu is equal to 0, and we have x1 is 2x2. This one tells me that x1 is equal to lambda plus 4 mu divided by 2 plus 2 mu. And this one tells me that x2 is half of x1. Then x2 will be lambda plus 4 mu, 4 plus 4. I simply divided this by 2. So at this point you have two options. One is to insert the value of lambda that you have from this equation. That makes your life easier. So if you want to look at this in the context of linear programming, in linear programming, you will find most of your answers here because you have a set of A multiplied by X is equal to B constraints, and probably they will help you to simplify your dual problem. So if we do that, then lambda is minus 1 over 2. So let's insert lambda here. It will be minus 0.5 plus 4 mu, 2 plus 2 mu. Then multiply both numerator and denominator by 2. So I just multiply by 2 over 2. It will be minus 1 plus 8 mu over 4 plus 4 mu. And then x2 will be half of this, which is minus 1 plus 8 mu divided by 8 plus 8. Alright, now let's see how our dual function looks like. So we don't have any lambda anymore, but we can find it by replacing the values in the Lagrangian. So it will be 4, 8 mu minus 1 square, 8 plus 8 mu square, plus 8 mu minus 1, 8 plus 8 mu, plus mu multiplied by 2, 8 mu minus 1, 8 plus 8 mu minus 2 square minus 2. So I encourage you to write down all of these steps for this problem so you can follow how we find this. Because if you recall, I just write the Lagrangian, it's x1 square plus x2 plus lambda multiplied by minus x1 plus 2x2 plus mu x1 minus 2 square minus 2. So I just inserted the values in this. So we have x1 square, we have x2, we have lambda, which is minus 1 over 2 multiplied by minus x1 plus x2, and we have mu by this. But the fact is this one is equal to 0, so we don't have this here anymore. So, if we solve both of these problems, I'm not going to go over the details, but so your dual problem is minimizing phi of mu, subject to mu is positive. So the answer to this is mu star is 0.59, and we already know that lambda star is minus 0.5. So if you insert these two inside your objective, it will be 636 over 1000. And if you solve your original problem, x1 star and x2 star will be 0.585 and 0.2925. If you insert them in the original objective function, it will be 0.636. So these two are equal. What it means that duality gap is equal to (636 minus 636) is equal to 0. Alright, so now you may ask, okay, what's the point of doing this? How this is helping us? The first thing is, here we could find the value of mu without going through the binding, non-binding stories. If you recall, we had to check whether the problem is binding or is non-binding. This is the first one. The second point is, as you can see, the dual problem is revisiting the structure of your original problem. What that means, it means that if you have some coupling constraints in the original problem, let's say in the original problem, in the constraint set, you have 2x1 plus 3x3 is equal to 4. And you have x1 plus x2 plus x3 and 2. So what the dual problem does, it somehow decouples these constraints. Because now you are not going to have the exact same constraints. You will only have, let's say, mu1, mu2. We are going to transpose the matrix, which was the coefficients of this. So it's like 2, 0, 3, 1, 1, 1. If you find A transpose, 2, 0, 3, 1, 1, 1. So as you can see from this matrix, you are changing the structure of your optimization problem. Where can we use that? We can use that when we are doing decompositions, when we are doing distributed optimizations. I probably will touch base on that one next week, so I'm going to talk about how this duality can help us if we have time to talk about Danzig word decomposition. So that's all for duality in nonlinear optimization. Thank you.